Hey guys, welcome to physics. All right, so today we're going to look at chapter 1, which is an introduction to physics. We're going to just kind of talk about the concept in this. We will have some additional resources, including ones made by me, where it'll go into how to solve things, all that good stuff, and explain more of the details for the different steps of solving problems. We'll get to that when we get to the additional resources tab. In the meantime, let's go ahead and get started, shall we? All right, so chapter 1, Introduction to Physics. Let's go. So section 1 is, what is physics? A lot of times kids have this idea that it is super duper complex and all that. And yes, part of it is. Sometimes it can be, but it's also around us every day. When you walk, you are experiencing the effects of physics. When you hold a pen, you are experiencing the effects of physics. So it's more than just the super complex stuff. It is literally all around you at every moment of every day. Now, first, just a little bit of intro to science and all that, because, physics is a type of science. So these are some of the steps that are common to the scientific method, which is just a series of steps used to conduct a scientific investigation. So first thing you have to do is make an observation about something in the world around you, and you might have to do some research about it in order to do the second step, which is formulate and test a hypothesis. Now, remember, a hypothesis is an educated guess, which is why you have to collect some data and do some research in step 1. Because if you're going to make an educated guess, you got to educate yourself on what's going on. So you observe something in the world around you. The sky is blue, plants are green. All right, I'm making observations. I'll ask a question, why are plants green? And then I will look up information that's already known about plants. From my research, I'm now educated on what is known in the subject, so I can now make an appropriate hypothesis, an appropriate educated guess. Sorry, it's a rainy day today, and you know how those just make you feel. So, plants are green. All right, I can make an educated guess. Maybe it's because they absorb green wavelength of light. And now I can go through and run an experiment to test my hypothesis. So once I run my experiment, I get my data from it, and I can interpret my results. So I go through, I collect it, my hypothesis proved to be incorrect, so now I can revise it. Once that, I can make my conclusion. So the conclusion is just the summary of what you learned from your experiment. It also does tell if your hypothesis was correct or incorrect. And in science, it is okay if your hypothesis is incorrect. A lot of times, scientists learn more from a wrong hypothesis than they do from a right one. So it's all good. All right, inferences. So an inference is a logical interpretation of your observations. It's not a conclusion. It is not saying this is what this means. It is an interpretation. So observations combined with inferences to help you come up with your hypothesis. So it's kind of that way that you connect ideas in order to come up with your educated guess. Again, it is not a conclusion. That is not what an inference is. It's more so, all right, plants are green, and I know that's related to the chlorophyll, so maybe it has something to do with the wavelength of light being absorbed. So I used what I learned and what I observed. So I observed plants are green. I learned that they have chlorophyll, which runs photosynthesis or absorbs light for photosynthesis. So I make a connection between the two. I interpret what that could mean. Again, this is just to help you build your hypothesis. Hypothesis and testing. So As we said, a hypothesis is a testable explanation based on scientific research. So we did our research. Sorry. We did our research. We came up with an educated guess, and now we're going to test that guess. We can't just say plants are green because my dog wills it. We can't test that. In scientific experimentation, you have to be able to test your ideas. So we always say perform many trials. Many experiments are needed to be performed in order to either confirm that your hypothesis is correct or refute it. The more trials you have, the more accurate your results become. If you just do a one and done, so you do one trial and that's it, and you base everything off that, what if something went wrong in that experiment that you didn't realize? What if there were other factors that, other factors that you weren't planning on that affected the outcome of your experiment? So you have to do many trials. And we always say that experiments must be controlled. And what that means is that we are only testing one variable at a time. This way, you know exactly what is different between your experimental group, the one you're testing, and the control group, the normal group. If there's only one thing that's different between all of them, all your groups, then you know what is influencing the change. So for instance, if I want to test my hypothesis that green light is being absorbed into the plants and that's what makes them green, what I can do is set up a series of experiments with a whole bunch of plants. Now I would want them all to be the same plant because different plants can react differently to different types of light or grow at different rates. So I'd want to use all the same plants. I would want to use soil from the same source, and they would have the same amount of it. They would receive the same amount of sunlight. They would be in an area with the same temperature. They would receive the same amount of water. Everything would be the same. I would treat them all identical to each other. The only difference would be maybe I would put a light filter around around the different plants. So for this plant, underneath this light, I might have a green filter, so only the green light goes through. For another, I might have a blue filter. For another, I might have a red filter. And one, I might have a yellow filter. And then, so all those are getting different types of lights, different wavelengths of light. I would also have one that's just exposed to regular light, whether it's a light bulb like the other ones or the sunlight, but I would want no filter on it. That's my control group. Why is it a control group? Because I know what should happen with that plant. It should grow at a decent rate. The others, those are my experimental group. I'm trying to see how the different lights affect their growth. And that brings us to variables. So we have two main variables, the independent variable and the dependent variable. So the independent is the one you're testing. So in other words, what are you doing differently in the experiment? Well, in the experiment we just talked about, I am choosing to use different light filters for each plant. That is what I am doing differently. That is what I am looking at. The dependent is going to change in response to your independent variable. In other words, what are you measuring? What are you observing? So I might be looking at either the plant growth or the plant pigmentation. So if does a plant under the blue light, does it start turning blue? Does a plant under the red light start turning red? Is it absorbing those wavelengths, and that's what's giving it its color? So it's whatever I'm choosing to measure or whatever I'm choosing to observe. All right, let's move on to section 2, physics and society. So, physics. Pretty much, in layman's terms, it is a science that includes and describes everything around us. And we already kind of mentioned that it's how you walk, how you hit a baseball, how you throw something, how airplanes fly, how boats float. All that is described by physics. How to do those things is all because of physics. So it includes technology, inventions, tools, buildings, etc. It includes our daily life. Even if you think, well, I'm not really big in tech, and so that means I'm not really big into physics. You walk, don't you? Blood moves through your veins, doesn't it? Neurons fire in your head, don't they? All that has some, or can be explained and described by, you guessed it, physics. So physics is everywhere. You do use physics every single day without realizing it. Any problem, anything that incorporates temperature, size, motion, position, shape, color, all of that can be described by physics. It is everywhere around us. Why does this shirt appear yellow? How is it that a dog can pull so hard even if it's a small dog? All that can be described by physics. In physics, we like to use models. Well, actually, pretty much every science, we use models. Now, what models are? They're simply any representation used to show the structure of a system. So it's any representation that helps you to understand something, whether it's a concept, a problem, etc. So it helps us to examine an idea and helps us to understand what's going on in there. Now notice I said any representation. A lot of times when we talk about models, kids picture the ones that are pictured down here. Like that's a cell and that's a bridge. We can tell that by looking at it, we can understand what's going on. But that's not all they are. Any kind of drawing that helps you to understand a concept, any type of chart or graph that helps you to understand a concept, any type of computer simulation, or even, yes, equations that help you to understand a system or a concept. Those are all models. And in physics, we're going to use a lot of equations. So we're using these mathematical formulas to help us understand what's going on within different systems of force, energy, electricity, etc. All right, section 3, units and dimensions. The first thing we're going to talk about is measurements. Yes, we gotta measure things. It happens. Now, measurements are very much essential to data in our experiments because they help us to get an idea of more than just, a number. It refers to different things. So even though we write them as numbers, there's so much more to it. It talks about quantity of a particular part of the system. So how much force, how much of this particular energy source. And it talks about dimension. So we see these in multiple different ways. Now, the reason why I'm not going to go into dimension yet is because it'll be easier when we have visuals. So quantity, how much of a physical quantity is there? Now, and like we said, that can be any number of things. If we're talking about fluid dynamics, we might want to know the volume of a liquid. We need to know how much liquid is there that takes up that whole space. It depends on units that the quantity are being measured in. Units are very, very important. You will always need to write down and keep track of your units. And I'll tell you right now in my class, if you do not have your units on an answer, if you just give me a number, you will lose points. Because units are very important. The units tell me what is it you're measuring, what is it that you're calculating, what are you looking at. So very important. All right, dimension. So this is what kind of quantity are we looking at? So the quantity tells us how much. The dimension tells us of what kind. So there are 5 main dimensions that are looked at. Length, so what's the distance between 2 points, mass, how much matter is there in this object, time, how long does something take to occur, temperature, what is the amount of heat energy required, and electric current. So how much energy, electric energy, is moved. We do use the SI units, which are the Systeme Internationale units. They are focused mostly on metric units. In 1960, the International Committee agreed on measurements to be used in all science. There are 7 basic units that describe a single dimension. Again, we'll get into some of that stuff later. We'll talk about different units as we approach different topics. Here are the 7 different units. We have mass, length, time, temperature, amount of substance, electric current, and luminosity, or luminous intensity. Now, we're not going to deal in my class right now with a whole lot of the luminous intensity and the amount of substance, the moles. What we're going to deal with is more so the other 5 that we already mentioned. Here are the main units. We have the kilogram, meter, second, Kelvin, mole, ampere, candela. These are the 7 main SI units that are used for each of these quantities. So mass, we tend to use kilograms. That's what we would consider our main unit. Length is meters, time seconds, temperature kelvins, the amount of substance is mole, electric current is the ampere, and the luminous intensity is candela. And this tells you the abbreviation for each one. Now, kg for kilogram and for meter. With time, a lot of times we'll just write S. We won't write S with the superscript A. In my class, we're just going to do the S, and so on, so on. Prefixes. Prefixes are used to describe very, very large or very, very small amounts within a base unit. So this can be, used with, if we don't want to write it in scientific notation, we can then do metric conversion in order to, instead of talking about 1,000 meters, I can do metric conversion and talk about 1 kilometer. So it helps us to kind of deal with these larger or smaller numbers if we use the prefix instead. Again, that's if you don't want to use scientific notation. Increase or decrease by a power of 10. That's the nice thing about the metric system. And as we already said, what system of measurement is it based on? It's based on the metric system. So these are just giving you some examples of the different prefixes used that are commonly used in the metric system and specifically in physics. Now, a base unit would be between these two. So let's say a meter or a gram. Let's say gram. So gram would be here. Kilogram, kg, would be times 10 to the third. A megagram, mg, would be times 10 to the 6th. A gigagram, big G, little g, would be times 10 to the 9th. Then we can also go smaller. Decigram is times 10 to the negative 1. Centigram, cg, times 10 to the negative 2. Milligram, mg, little m, times 10 to the negative 3. Micro, nano, pico, femto. Now, when we get especially to things like electricity, you're probably going to see these ones more often, the micro and nano and pico, especially micro. So micro is times 10 to the negative 6, nano times 10 to the negative 9. Those are going to be the 2 main ones, especially micro. Now you notice with micro, it's got this weird U shape. That's actually the Greek letter mu. your measurements need to be consistent dimensionally. So that means that you can't have different units. You have to try and get everything to the same unit. And that's where something called dimensional analysis comes in. So it's a type of calculation that is written in terms of the dimension. Because if you do not put everything into matching units, you will not get a correct answer. It's just not going to happen. So this down here, we want to know how many seconds are there in a day, and it talks about how to go through and solve it. We have a whole video on this, so I'm not going to really discuss it here in the chapter discussion. And here's just an example. So 4 millimeters equal how many meters? Now from the chart, we know that milli, we said, was times 10 to the negative third. So we have 4 millimeters is what we're starting with. 1 millimeter is equal to 10 to the negative third. You could write it as 1 times 10 to the negative third if you wanted to, but it's the same answer. It equals 0.004 meters, or we could take that, write in scientific notation, 4 times 10 to the negative third meters. Again, we have a whole video on this, so don't stress out too much. So just a little bit on basic math for physics. We will have lots and lots of equations. It's going to happen, I'm sorry. But the reason why is because equations are mathematical expressions that relate the physical quantities. So we said physical quantities, we've used that term before. What is it? It's a property of a physical system that can be measured. So what we do with these equations is we're able to take these different properties, these different physical ideas like length and time, and combine them in order to understand how they relate to each other. So they can be rearranged to solve, and equations can be rearranged to solve for numerical variables. So here we have the speed equation. Speed equals distance over time. I can rearrange it. Time equals distance over speed. Rearrange it again. Distance equals time times seconds. So even though this right here, S equals D over T, is the main speed equation, we can rearrange it to solve for the other variables. Let's talk a little bit about quality of measurements. Accuracy is how close your measured values are to the actual value versus precision, how close together your values are to one another. So accuracy, how close are they to what they should be, and precision, how close are they to each other. So here we have 4 bullseyes. Notice all 4 dots are together in the bullseye. That means that all the dots are where they should be. With a bullseye, you're trying, or let's say this is darts, you always want to get them in the bullseye, that's the most points. So they're all where you would want them to be, so they're accurate. They're also precise because they're all close together. Here, they're nowhere near the bullseye, but they're still together. So it's not accurate, but it is precise. Here, they're close to the bullseye, but they're not together. So it's accurate, but not precise. And here, they're not close to the bullseye, and they're not together. So not accurate and not precise. Significant figures. So what this is it looks at digits in a measurement that are actually measured plus the first digit that is estimated. So significant figures help you to be more accurate in your measurements and as well as in your calculations. So a pencil is 499.2. I'm not sure what that's supposed to be, what unit that's supposed to be. That's an incorrect unit, I apologize, but whatever unit is that long. So it has 4 sig figs. 4, 9, 9, and 2 are all significant figures. The first 3 are measured, and the last one is the estimated one. And again, we have a whole video on how to figure out significant figures as well as the rules, so don't stress too much right now. But we do have at least a little brief on the rules. So there will be a sheet that will be put out online for you to look over in terms of understanding what the rules are for whether or not a 0 is significant. when you multiply or divide values, the answer is going to, since you're not actually measuring the answer, you're calculating it, you have to follow specific rules to get the correct number of sig figs. So the answer should always have the same number of sig figs as the least accurate value. So the value that you are starting with that has the least amount of sig figs, that should be the same number of sig figs in your answer. So you probably have to round a little bit to get there. For addition or subtraction, the answer should have the same number of decimal places as the value with the least amount of decimal places. So whichever value has the fewest decimal places going into the problem, match that with your answer. Again, we're gonna have a video on how to solve these. I'm just trying to get the information out there. So when solving, variable with the least amount of sig figs determines the sig figs for the answer. So here we have a room. It is 4.2 meters by 5.232 meters. What is the area of the room? Well, we know area is length times width. Now, if we look at this, we multiply 4.2 times 5.232, we get 22.00. We look at the numbers. 5.232 has 4 significant figures. 4.2 has 2 significant figures. 2 sig figs is less than 4 sig figs. We're going to take this, round it, and we get our answer of 22 meters. All right, now here are those additional resources that we mentioned. The Science in Pajama ones are actually videos that I make myself. So I'm not going to go all the way into them. Just kind of show you a little bit. We're not going to watch them here in this video. So I have one on the scientific method. Sorry, hit the wrong button. You can either watch it within the presentation if you wanted to when you're watching this, or when you go to the Prezi, you can either watch it in the Prezi or you can just go follow the link. Experimental variables, metric conversions, scientific notation, accuracy versus precision, significant figures, and dimensional analysis. So we have videos done by me to explain all of those. Oops, I'm so sorry about that. Hit the wrong button. All right. And other videos are ones that I get from YouTube. So we have Khan Academy talking about the scientific method, Bozeman Science, what is physics, the chemistry solution, dimensional analysis, crash course, unit conversions and significant figures, and the organic chemistry tutor on significant figures. So I definitely recommend checking some of these out. They'll help you to understand the concepts. Yes, we will talk about them in class as well, but this way you just have additional resources because, you know, those are always good. Anyways, I hope this helps. I hope this, you know, made you feel a little bit better about science and all that. But in the meantime, you guys, just take care, stay awesome. If you have questions, hit me up in our Google Classroom, email, our actual classroom, or, no, that's pretty much it. So yeah, I'm sorry, I'm a little bit out of it. I told you it's that rainy day feeling. But also I will post the link for this Prezi into the video description for this presentation so that you can have access to all of these links and the additional resources. All right, guys, until next time, stay awesome, stay amazing, stay safe, and I will talk to you later. All right, guys. Bye-bye.